SQL is still the most commonly used big data computing language, but did you know that SQL often runs very slowly, seriously wasting hardware resources? Take a look at a few cases. A bank's anti-money laundering preparation, with 3.6 billion rows of data. An 11-node Vertica cluster runs for 1.5 hours. A certain e-commerce funnel operation with a data scale of 300 million rows, Snowflake's medium 4-node cluster takes more than 3 minutes, and cannot get a result. A certain spatiotemporal collision task, with 25 billion rows of data, a ClickHouse 5-node cluster runs for 1,800 seconds. The data volume of these cases is not very large, ranging from a few gigabytes to several hundred gigabytes. However, the performance of SQL is not satisfactory.
So, are these tasks too complex and can only be so slow?
No. These tasks have significantly improved performance after being rewritten in SQL. Anti-money laundering preparation calculation, SQL single machine only takes 26 seconds, surprisingly turning the batch job into a real-time query. Funnel operation, SQL single machine finishes in 10 seconds. The spatiotemporal collision task, an SQL single machine only takes 350 seconds. After switching to SQL, not only does the computing performance increase by an order of magnitude, but the hardware resources are also reduced, turning the cluster into a single machine. In fact, even the code is shorter.
Why can't SQL achieve this performance?
Because SQL cannot write low-complexity algorithms. For example, to find the top 10 from 100 million pieces of data, SQL is written with the word order by, which means sorting is required. If we really do big sorting of 100 million records, the computational workload would be huge. In fact, as long as we keep a small set of 10 members and continuously compare and replace members in the small set when traversing 100 million data, the computational cost is 8 times less than that of big sorting. Unfortunately, SQL does not have an explicit set data type, and cannot describe such a calculation process, and can only rely on database optimization. Fortunately, almost all databases can optimize this and won't be foolish enough to do big sorting. But what if the situation becomes slightly more complicated? For example, if we change the requirement to find the top 10 within groups, the SQL statement would look like this. This is very different from the previous method of getting the top 10 from entire set. We need to first use the window function to create a sequence number within groups, and then use subqueries to filter out records that meet the conditions, which is a bit convoluted. Anyway, there is still an order by here, and the operation logic is still sorting. In actual testing, it is found that for the same amount of data, Oracle calculating top 10 within groups is dozens of times slower than calculating top 10 of the entire set. Theoretically, only adding a grouping operation should only be slightly slower. Oracle is likely to have performed sorting or even external storage sorting, and the database optimization engine may become fainted when faced with slightly more complex situations. It can only execute according to the logic of SQL honestly, resulting in a sharp decline in performance. Of course, perhaps one day the database will evolve again, and encountering such a situation, it can also optimize it. But there are always more complex situations, and the evolution speed of database optimization engines is very slow. The cases mentioned earlier all have a certain degree of complexity in business requirements, with small amounts of data but large amounts of computation. SQL cannot write good algorithms, and database optimization engines are also unreliable. For example, calculating the conversion rate of e-commerce funnel. This is a typical calculation problem related to object events, which is very common and accounts for more than half of the scenarios in data analysis business. The objects in this type of computation, besides e-commerce users, there are many others, for example, gamers, bank accounts, mobile phones, vehicles, etc. Objects usually have a unique ID, and all events involved are recorded under this ID. For example, call records of mobile phones, user operation logs, transaction records of bank accounts, etc. The task of object event problem is to calculate a certain aggregation value for each event that meets certain conditions in each ID, and then perform overall statistics on all IDs. Specifically, funnel analysis involves identifying the maximum number of steps each user can reach in a given sequence of steps, within a short time window. For example, given 3 steps, the aggregation value to be calculated for browsing products, viewing details, and confirming order is, each user can reach to a few of these 3 steps in sequence within 3 days. With the maximum number of steps per user, through simple counting, it can be calculated the overall number of users who have reached each step, and then analyze which step has the most severe user churn rate. To clarify the difficulty of using SQL to solve this problem, let's first look at several characteristics of object event calculation. There are a large number of IDs, ranging from tens of millions to billions. There are not many events with the same ID, ranging from a few to several thousand. Thirdly, the calculation of events within the ID is complex, with multiple steps and correlations between events. There is no correlation between IDs during calculation. Let's take a look at the difficulties of implementing this type of operation in SQL. Firstly, when performing association calculations for events within an ID, complex big table joins may occur. These computational tasks involve multiple interdependent event records. SQL has weak support for cross-row operations, and requires joining multiple rows of records to one row for further operations. Moreover, the events involved in the operation have conditions, and generally need to be selected using subqueries before join. The more events involved in the calculation, the more subqueries participate in join. For example, the 3-step funnel in the figure involves multiple records of ID 1. First, use multiple subqueries to filter suitable event records, then join multiple rows of records into one row in order to perform further operations. These subqueries also have dependencies. For example, the second step event needs to be searched based on the first step event, and the subqueries themselves also need to be calculated using join. These subqueries are all based on huge event tables, which are already difficult to perform joins on big tables. Joins have to be repeated multiple times, so running slowly is not surprising. Running crashes are also normal. When continuing to calculate aggregate values, it will also involve group by for big result sets. Because in the expected outcome, each ID corresponds to one set of aggregated values, the result of join does not have this feature, and the same ID may result in multiple records. At this point, it is necessary to perform another group by for the ID. The number of IDs is very large, and the grouping performance of this big result set is very poor, and the parallel computing effect is also not good. Sometimes, the calculation goal is to count IDs and group by degenerates into count distinct, but the complexity order of magnitude remains unchanged. Feel it. This is a 3-step funnel analysis written in SQL, which includes multiple ID-related big table join, group by, and count distinct. In fact, as long as the aforementioned features are utilized, solving the problem of object events is not difficult. We can sort events by ID, with few events for each ID, and read all events of one ID into memory at a time. It is easy to implement such complex calculations using procedural languages in memory. Because IDs are unrelated, in-memory association operations are only performed within the event range of one ID, and there will be no big table join. It will complete the calculation of one ID aggregation value each time, and there is no need for group by ID in the future. Count distinct will also become a simple count. This algorithm not only requires less computation, but also occupies less memory, making it easy to parallelize. Unfortunately, using SQL cannot implement such an efficient algorithm. This is mainly because SQL lacks discreteness and cannot implement procedural complex cross-row operations, so only join can be used. Moreover, the set of SQL is unordered, and even if deliberately stored in an ordered manner, it cannot be utilized. So, how does SPL solve these problems? Let's first look at the top-N problem. SPL understands top-N as aggregation calculation similar to sum and max, except that the return value is a set. This is equivalent to implementing the efficient algorithm mentioned earlier. The code is written as follows. There is no word order by in this statement, and it does not perform a big sorting and will instead use a small set algorithm. Moreover, the writing of the top 10 within groups here is basically the same as that of the top 10 of the entire set, except for the addition of grouping key. Then let's look at the object-events problem, and it is easy to implement the efficient algorithm mentioned earlier using SPL. SPL's set is ordered, deliberately ensuring storage order, and provides ordered cursor that can read event data of one ID at a time. The SPL syntax strengthens discreteness, making it easy to write code for multi-step cross-row operations using natural thinking. This is the code for implementing the same funnel analysis in SPL. Here, all events of one ID are read in each time, and complex judgment logic is implemented using 4 lines of code, from A9 to A12. Finally, when grouping and counting are done in A12, simple counting is enough, without the need to consider deduplication. SPL can also solve the long-standing problem of join in SQL. The definition of join in SQL does not involve primary keys, but almost all business-meaningful joins are related to primary keys. SQL cannot utilize this feature. The use of bilateral hash join algorithm not only requires a large amount of computation, but also has uncontrollable performance in external storage and clustering. SPL redefines joins by categorizing them, which can fully utilize primary key features to reduce computational complexity. Not only is the calculation fast, but there are also no uncontrollable issues. As a result, the performance of association table operations in SPL often exceeds that of wide tables in SQL. The deeper reason for the poor performance of SQL lies in the lack of necessary data types and basic operations in its basic relational algebra. This theoretical problem can only be improved to a limited extent by engineering methods, and cannot be eradicated. Distributed computing can sometimes improve performance, but the cost is too high. SQL tuning has limited effectiveness, and is not effective for complex situations. Tuning can indeed adopt certain efficient algorithms by changing the execution path, but many high-performance algorithms do not exist at all in SQL. Writing high-performance code using UDF is feasible in principle, but the cost is too high and the operability is poor. Cluster environments can also bring complex distribution and operation issues. Moreover, if the database storage scheme cannot be changed, it is difficult to speed up using UDF alone. SPL adopts innovative discrete dataset theory with more data types and operations. It can encapsulate more high-performance algorithms. The algorithms marked with asterisks here are all original creations of SPL. With these foundations, it is easy to write low-complexity code, fully utilize hardware resources, and achieve high-performance computing that is orders of magnitude faster than SQL. SPL actually provides cluster computing capabilities, but in SPL's performance optimization cases, most scenarios where a single machine is sufficient, there are few opportunities to experience cluster functionality, so SPL hardly promotes distributed capabilities. Reducing computational complexity is the key to improving big data computing performance, but many low-complexity algorithms cannot be implemented in SQL, and complex situations cannot rely on database optimization engines. SPL can facilitate the writing of high-performance algorithms. In many performance optimization cases, SPL single machine can achieve performance orders of magnitude faster than the original SQL cluster, effectively reducing hardware resources. It is a truly green and low-carbon technology. SPL is now open source. Welcome to download and try it out.